Hey everybody, and welcome to Pre-Calculus Algebra Lecture 15, Part 2. Hopefully the last part of Lecture 15. We're going to start today by talking about transformations of power functions. We had an introduction to polynomials in general and to power functions in Part 1 of this lecture. We're going to pick up from there and do transformations of power functions. This one asks us to graph f of x equals x plus 2 to the fourth minus 3. And this function is just a set of transformations on the power function f of x equals x to the fourth. So if I'm graphing this, the first thing that I'm going to do is graph the power function that this is a transformation of. And that's going to be f of x equals x to the fourth. We invite our old friends, -1, (0), and +1. And we remember that if the exponent is even, then the point 1, 1 is a point on the graph, and the point -1, 1 is also a point on the graph, as is 0, 0. Let's see, did that all fit in the picture? Yep, sure did. And this is the skeleton upon which we hang the graph of f of x equals x to the fourth. The next thing that I'm going to do is my vertical or horizontal stretching. And there isn't any stretching or compression. The coefficient of x to the fourth, a, is going to be 1. So no stretching vertically or horizontally. So I go right to my vertical and horizontal shifts. And the first thing that I'm going to do is address my horizontal shift. And remember how deceptive horizontal shifts are? They do exactly the opposite of what we think they should do. We see a +2 here and we think, aha, 2 units in the right direction. This is going to be a horizontal shift left. By 2 units. So we take the vertex 0, 0, and we move it left 2 units. So that it's at -2, 0. Here's a point on our graph. We take the point 1, 1 and move it to the left 2 units. So we go 1 unit to the left, x is 0. A second unit to the left, x is -1. So there's a point on our graph. And this point, -1, 1, we shift it 2 units to the left. So essentially what we're going to do is subtract 2 units from the x coordinate. -1 minus 2 is -3. Or look at it this way. On the x-axis, Here's x equal -1. If we go to the left 2 units, we're going to go 1 unit to the left, 2 units to the left. That brings us at x equal -3. So -3, +1 is going to be a point on our graph also. The point -3, 1 corresponds to the point -1, 1 on the original graph. The point -2, 0 corresponds to the point 0, 0 on the original graph. The point -1, 1 corresponds to the point 1, 1 on the original graph. We haven't changed the size or shape of the graph. We've just moved the whole thing 2 units to the left. And we hang our graph on this skeleton now. Excellent. Excellent. So this is the graph of f of x equals x plus 2 to the 4th. We're not done. We have to incorporate this transformation also. It's a vertical shift. And the vertical shift, that's our friend. It does exactly what it's telling us that it should do. We see -3 here and we think, that means it should go down 3 units in the y direction. And that's exactly what happens. The vertical shift, that's not deceptive at all. So what does that mean? It means we're going to take every point on this graph and move it down 3 units. Son of a gun. Son of a gun. How are we going to do that? I think I'll make this my x-axis. So here's my origin, 0, 0. And this point, -2, 0, the vertex, is going to go down 3 units. So we start at -2, 0, and we go down 1 unit, we go down 2 units, we go down 3 units. So y is now -3. Now let's move this point down 3 units. It was at x equal -1, y equal +1. That's this point right here. It was at -1, +1. But we have to move it down 3 units. Go down 1 unit, go down 2 units, go down 3 units. And there we have the corresponding point on this graph. And that's going to be x equal -1, y equal -2. Forgive me, I'm just trying to reduce some of the clutter in this graph. Now we've got to take care of this thing. And there are two ways we can do this, just like there were two ways that we could do the other 2 points. One, we can take this point, which is negative 3, 1, right here, negative 3x, 1y, and move it down 3 units. Here's 1 unit, here's 2 units, here's 3 units. So we are at the point negative 3, negative 2. Now, how else could we have gotten this point? We could have taken the y coordinate, and since we're going down 3 units in the y direction, we could have subtracted 3 from the y coordinate. Keep the x coordinate the same, and subtract 3 from the y coordinate. 1 minus 3 is negative 2. That gives us the y coordinate of this point. And here is the skeleton upon which we hang our graph. And there we have it. The finished product f of x equals x plus 2 to the 4th minus 3. There it is. Now let's do one more of these, and let's do a power function whose exponent is on. Our next project, graph the variation of the power function. F of x equals 1/2 x minus 5 to the 5th minus 2. And to graph this, the first thing I'm going to do is graph the power function of which this is a variation. And I'm going to graph, you know what? I did 2 versions of the power function. I did x to the power of n, and I also did a times x to the power of n. We know what both of those look like. So I think what I'm going to do is I'm going to start with f of x equals 1/2 x to the 5th. In our discussion of graphing power functions, we had some experience graphing f of x equals a times x to a power. And there's no big mystery on how to do this. We enlist the aid of our friends -1, 0, and +1. X equal -1, x equals 0, x equal +1. And when x is 0, 0 to the 5th is 0. So we have 1/2 times 0 is 0. This is a point on the graph. And when x is 1, we have 1 to the 5th, which is 1 times 1/2. Whoops, whoops, whoops. So we have the point 1, 1/2. X equal 1, y equal 1/2. And when x is -1, we have -1 raised to an odd power, so that's going to be -1 times 1/2. So that's -1, -1/2. There we have our skeleton. And we hang the graph on it. F of x equals 1/2 x to the 5th. Now all we have to do is look at our horizontal and vertical shifts. We'll do our horizontal shift first. I think the y coordinates stay the same here, but the x coordinates, they get shifted. Remember the deal with the horizontal shift? It does exactly the opposite of what we think it should do. We have -1 here, and we think, aha, shift horizontally to the left because this is negative. No, if this is a negative here, we shift right. So we shift every point on this graph 1 unit to the right. It's as if we grabbed this graph, picked it up off the board, and moved it 1 unit to the right and put it back down. That's essentially what we're doing. This point is at x equal 1, y equal 1/2. If we move it 1 unit to the right, we go from x equal 1 to x equal 2. And we have the point x equal 2, y equal 1/2. We just took this point at x equal 1 and moved it 1 unit to the right, so now it's at x equal 2. We're going to do the same thing with this point. This is at x equals 0, y equals 0. It's a horizontal shift, so y won't change. Y is going to continue to be 0, but the x coordinate is shifted to the right. I beg your pardon. Shift right 1 unit. That must have been confusing. I apologize. So let me just go back and address this point. It's a horizontal shift 1 unit to the right. Since it's a horizontal shift, the y coordinate doesn't change. It's going to remain 1/2. We're going to take the x coordinate, which is 1, and go 1 unit to the right. That brings us at x equal 2. So the x coordinate is going to be 2. We'll do the same thing with this point. It's a horizontal shift, so the y coordinate won't change. The y coordinate will be 0. And we're going to move this point 1 unit to the right, which means we go from x equals 0 to x equal 1. The new point is going to be x equal 1, y equals 0. And then this other point, it's a horizontal shift, so the y coordinate won't change. It's going to continue to be 1/2. The x coordinate here is -1, but if we start at -1 and go 1 unit to the right, we're at x equals 0. So the new point is going to be x equals 0, y equal -1/2. Ah, look at that. A more beautiful graph I never saw. Wonderful. Oh, but we're not done yet. We are not done yet. We have to account for this transformation too, and this is a vertical shift. And with a vertical shift, it always tells us what we think it's telling us. -2, that means 2 units down in the negative y direction. So we're going to pick this graph up off the board and just move it down 2 units. Another way of thinking of this is we're going to subtract 2 from every x coordinate. The shape of the graph is not going to change. Just its position in the xy plane. This point is x equal 2, y equal 1/2, and we're going down 2 units. So we're going to start at y equal 1/2 and go down 2 units. Or we can think of this as subtracting 2 from the y coordinate. 1/2 minus 2 is -3/2. So this point is 2 -3/2. Son of a gun. That's way below the x-axis, isn't it? Well, that's okay. This point, we're going to keep the x coordinate the same because this is a vertical shift. Only y will change. And we're going down 2 units. We're starting at y equals 0, and we're going down 2 units. 0 minus 2 is -2. So this is the point 1 minus 2. And finally, we have to account for this point. We're moving it down a vertical shift, so x won't change. X is still going to be 0. But we're going to start at y equal -2, and we're going to go down 2 units. -1/2 minus 2, let's see, that's the same as -1/2 minus 4/2. -1/2 minus 4/2 is -5/2. So this becomes the point 0, -5/2. Oh, and Molly, and how does this now relate to the x-axis? Let's see. This is -3/2, -2, -3/2, -1, -1/2. Wow, when you look at that, our x-axis is way the heck up here. There's our origin. This is our graph after it's been transformed and transposed. And again, this is the graph f of x equals 1/2 x minus 1 to the 5th minus 2. I'll clear some of this clutter off the board so that we can look at this for a second or two and just admire our work. You might have noticed that when we graphed the transformations of our power functions, we didn't pay any attention to where these power functions intersected the x-axis. We didn't try to find the x-intercepts at that point. And part of the reason was that we weren't really prepared to tackle that part of the project. We're going to turn our attention right now to the x-intercepts of a polynomial function, which our author calls real zeros. And here's how our author defines a real zero. The author says a real number r is a real zero of a polynomial f of x exactly when f of r equals 0. So a real zero, oh, and you know what? I need to underline this. I'm defining real zero of a polynomial. So a real number r is a real zero of the polynomial f of x exactly when we can plug r into the polynomial and get 0. Exactly when f of r equals 0. Well, let's see. F of x is the same as y. So a real zero of a polynomial is any value of x that makes the polynomial 0. Any value of x that makes y equal 0. And isn't that where the graph of the polynomial crosses the x-axis at y equals 0? So let's make this remark. The real zeros of a polynomial, they're exactly the same thing as the x-intercepts. So if we find the real zeros of a polynomial, we're going to know exactly where the graph of that polynomial crosses the x-axis or hits the x-axis. Now, let's do an example. Here's a polynomial, f of x, and watch what happens. If I plug -1 into this function, I get -1 squared plus 2 times -1 plus 1. So let's see. -1 squared is +1. Minus 2 is -1. Plus 1 is 0. Is -1 a real number? Yes, it is. And when we plug -1 into f of x, we get 0. So r equal -1 is a real zero of f of x equals x squared plus 2x plus 1. And this is also the same as saying this. Equivalently, the graph of f of x intersects the x-axis at x equal -1. So this real zero, -1, is also an x-intercept of the graph of f of x. As a matter of fact, if we were to graph f of x, this is what we would get. I apologize, I'm making a mess out of this thing. I'm still making a mess out of this thing. There we go. At x equal 1, x equal -1, the graph of f of x equals x squared plus 2x plus 1 intersects the x-axis. X equal -1 is a real zero of this polynomial. X equal -1 is also an x-intercept of the graph of this polynomial. Now this term, I'm not really accustomed to seeing it. And when I first saw it, I thought, real zero? Now, typically, I'm accustomed to seeing the expression the zero of a polynomial, or the zeros, plural of a polynomial. But in the book, they talk about real zeros, and at first I thought, real zero? Do we have to say real zeros? And you know what? I like what the author does here. The author has a very good point. And I'm going to give an example which shows why our authors actually have a great deal of merit in calling these things real zeros. Real zeros are real numbers that make a polynomial equal to 0. And real zeros are those points on the x-axis where the graph of the polynomial intersects the x-axis. So a real zero is a real number that makes the polynomial 0. And a real zero is a point on the x-axis where the graph crosses the x-axis. A real zero is an x-intercept of a polynomial. And let's look at a case in point that will show why our authors are actually onto a good thing here when they call these things real zeros. Let's give this example some consideration. F of x equals x squared plus 1. And here's what I'm going to do. I'm going to take the imaginary number or the complex number I, and I'm going to plug it into F. So where I see an x, I'm going to plug in I, and I have I squared plus 1. Well, what is I? Isn't I the square root of negative 1? So if I square if I square I, I'm going to get negative 1. I'm justified in saying that I is a 0 of my function f of x. I is a 0 of f of x. In other words, I is a number that we can plug into f of x and get 0. But I is not a real number. It's an imaginary number or a complex number, but it's not a real number. So I can't say that I is a real 0. I is not a real 0 of f of x. And we might say, well, so what? It's still a number that we can plug into f of x and get 0. And we're right. So why the big fuss about whether or not I is a real 0 or not? Consider the graph of f of x equals x squared plus 1. And here it is. This is the graph of x squared plus 1. What are the x-intercepts? Well, there aren't any. The graph doesn't cross the x-axis. And this is exactly the point that we're getting at. Only real zeros, only real numbers that are zeros of a polynomial correspond to points on the x-axis where the graph of the polynomial crosses the x-axis. I is not a real number. So even though it makes f of x equal to 0, and I is a 0 of f of x, I does not correspond to any point on the x-axis where the graph of f of x crosses the x-axis. And how could it? The x-axis contains only real numbers. If we try to find I on this x-axis, we're not going to find it. It ain't got one. The x-axis and the y-axis both only have real numbers. So our authors are onto a good thing here, being very deliberate in talking about real zeros. A real 0 is a real number that makes the polynomial 0. And those real numbers, those real zeros, correspond to points on the x-axis where the graph intersects the x-axis. A number that's a 0, but it's not a real 0, is not an x-intercept of the polynomial. We have a 0 here, I. It's a 0 of the polynomial, but it's not a real 0 because I isn't a real number. So this does not give us an X-intercept of the polynomial. The only zeros that give us X-intercepts of a polynomial are the real zeros. And that's why our authors are making such a fuss about this. The whole reason that they're talking about zeros of a polynomial in the first place is so we can find out where the graph crosses the x-axis and plot the x-intercepts. So our interest in zeros of a polynomial is pretty much restricted to real numbers, points on the x-axis, where the graph crosses the x-axis. There are zeros of a polynomial that are not real numbers, and these zeros don't correspond to an x-intercept of the graph. So that's what this bit about real zeros is all about. Speaking of real zeros, I'm going to tell you an important fact about real zeros. What I'm about to tell you is actually true for all zeros of a polynomial, but I'm going to restrict the scope of our conversation here to real zeros. And here's the fact. A real number r is a real zero of the polynomial f of x exactly when x minus r is a factor of f of x. Now that tells us two things. It tells us if f of r equals 0, then x minus r x minus the real 0 is a factor of the polynomial f of x. And it tells us something else too. It tells us if x minus r is a factor of the polynomial f of x, then r is a real 0. So this is a two-way street here. If f of r equals 0, then x minus r is a factor. And it says if x minus r is a factor, then f of r equals 0. It works both ways. This is a very underutilized and very unappreciative, this is a very underutilized and very unappreciated piece of information. My students in calculus, for the most part, probably knew this at one time, but they were told about this, and then after a day or two, they were never given an opportunity to use it, so they've forgotten about it. And that's exactly the way I was when I was a student in calculus. It was something that would have been very helpful for me to know, but I didn't know it. And I'm sure somewhere along the line, I had been told about this in an algebra class, and maybe we worked with exercises that highlighted this point for a day or two. And then I didn't see it again for a long time, and not only did I forget about it, I forgot that I ever knew it in the first place. But this is a very underutilized and very underappreciated piece of information. Because sometimes we want to factor polynomials and we look at them and we think, what? How on earth are we going to factor this thing? And almost always it has to do with a polynomial that has degree greater than 2. If we have a second degree polynomial, pretty much we can factor that if it can be factored. And if it can be factored but we can't factor it, we can use the quadratic formula to get the roots or the zeros of that polynomial. There is sort of an analog for third degree polynomials, an analog of the quadratic formula, but it's much more complicated. And it's complicated enough that when I was exposed to it, I thought, you know, this thing's so complicated, it's more trouble than it's worth. I don't want to know it. And there's even a sort of an analog for fourth degree polynomials, how to factor those, find the roots or the zeros of those. But that pretty much takes 2 or 3 pages of writing. It's very complicated, definitely not worth my while to get familiar with. But I might be in a situation where I need to factor a fourth degree polynomial or a third degree polynomial. And this piece of information is often a lifesaver. Let's look at an example or two, okay? Suppose that I want to factor something like this. It's a third degree polynomial. And at first I think, well, this shouldn't be too hard. But I look at the coefficients and I say negative 19, 30. What on earth do negative 19 and 30 have in common with one? What kind of a relationship is there between negative 19 and 30? I have no idea how to try to factor this thing. So here's what I'm going to do. I'm going to consider the whole number of factors of the constant term. Well, this has no shortage of whole number factors. What do we have? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15. There are a lot of whole number factors. I'm going to take these one by one and I'm going to plug them into my polynomial function. Why is that? Because if I can find one of these numbers that makes the polynomial 0, then I know that x minus that number is a factor of this polynomial. And did you see that? Just for reinforcement. If we find a number that we can plug into the polynomial and make it 0, then x minus that number is a factor. So, well, let's try 1. 1 minus 19 is negative 18. Plus 30 is 12. No, that's not 0. Scratch negative 1, 1. Try negative 1. Negative 1 cubed is 1. No, negative 1 cubed is negative 1. Minus 19 times a negative 1. So that's negative 1 plus 19 is 18. Plus 30 is 48. No, we don't get 0 with plus 1 or minus 1. Let's try 2. 2 cubed is 8. Minus 38 is negative 30 plus 30. Ooh, we get 0. F of 2 equals 0. So that means that x minus 2 is a factor. Things just got a lot easier. But what would have happened if we had plugged in negative 2? Negative 2 cubed is negative 8. Negative 19 times negative 2 is plus 38. So negative 8 plus 38 is plus 30. Plus 30 is 60. Well, we don't get 0 if x is negative 2. What about x equal 3? 3 cubed is 27. Let's see, 3 times 19, holy moly, negative 57. Plus 30, 27 plus 30 is 57, minus 57 is 0. F, when we plug in 3, we get 0. So that tells us that x minus 3 is a factor. Now we could probably figure out the remaining factor based on what we already have. As a matter of fact, let's do that. Let's do that. We have two factors. F of x equals x cubed minus 19x plus 30. And we know that that's equal to x minus 2, x minus 3, times one other factor. The fact that the polynomial is of degree 3 means we expect to have 3 factors. Well, let's see. Probably we're going to have an x here. X times x times x is x cubed. That looks good. And we're going to have a constant here. Whatever we put here has to multiply by negative 3 and negative 2 to give us plus 30. Negative 2 times negative 3 is plus 6. So whatever goes here has to multiply by plus 6 to get 30. So I say plus 5. 5 times negative 3 is negative 15 times negative 2 is plus 30. This is our factorization right here. Now, could I have found this factor the way we found the first two? Sure. I move on from 3 and minus 3 and plug in 5 and negative 5. If I plug in 5, I get 125 minus 95 plus 30. So this is 155 minus 95 is positive 60. That's not 0. Plug in negative 5. We get negative 125 plus 95 plus 30. When we plug in negative 5, we get 0. And that means f of negative 5 equals 0. That tells us that x minus whatever this is, in this case it's x minus a negative 5, is a factor. Well, what's x minus negative 5? It's x plus 5, right? That's our other factor. Now, if we had to start here and blindly try to figure out how to factor that thing, good luck, because we need it. But we know something. We may have been taught this years ago and just forgot it, or maybe we never knew it at all. But this is a good thing to know. If we can find a number to plug into a polynomial and make that polynomial equal to 0, like right here, then x minus that number is a factor. And at times, that's going to be a helpful piece of information. Most people who have been taught that forgot it 2 weeks after they learned it and have never used it since and can't use it because they don't even remember that they ever knew this. But it's a very helpful piece of information. This looks complicated, but it's not. Find a polynomial whose real zeros are 1, 4, and 5. Now, I'll start off by saying that there's more than one correct answer for this. As a matter of fact, there are infinitely many correct answers. Let's get the simplest polynomial that we can that has real zeros of 1, 4, and 5. And here's how we do it. We recognize this fact. If r equal 1, r equal 4, and r equal 5 are real zeros of f of x, then x minus 1 is a factor. X minus 4 is a factor. And x minus 5 is a factor. What's the simplest polynomial that we could construct that has these three things as factors? Just the product of these things, right? This is a polynomial. I'm going to leave it in that form. If they ask us to multiply it out, I guess we'll have to. But I think this is probably the form that they're looking for as an answer. And let's do one more just like this, just to make sure that we can avoid what might be a common mistake. Similar exercise, but with a slight twist. Find a polynomial whose real zeros are 2, -3, and 6. And we recognize that if r equal 2, r equal -3, r equal 6 are real zeros of a polynomial f of x, then r minus 2 is a factor. R minus -3 is a factor. And what does that really mean? It means that r plus 3 is a factor. And then finally, r minus 6 is a factor. So we have a polynomial that has these three factors. Oh my goodness, I'm being an idiot. Our function is f of x, so x is the variable. If r equal 2, r equal negative 3, r equal 6 are real zeros of f of x, then x minus 2 is a factor. X minus a negative 3 is a factor. And x minus 6 is a factor. So we have x minus 2, x plus 3, x minus 6. There's our polynomial. And I just want to make sure that my ineptitude didn't sabotage the subtle point that I was trying to make. If r equal negative 3 is a real zero of f of x, then x minus that number, x minus negative 3 is a factor. And that's going to give us x plus 3 as a factor. Still speaking about polynomials, we're now going to talk about the multiplicity of roots. What did I just say? Don't worry about it because I have it written right up here. A real zero r of a polynomial f of x has a multiplicity of m, where m is a positive whole number, has a multiplicity of m exactly when x minus r to the m power is a factor of f of x. So first of all, note that r is a real zero of the polynomial f of x. Second, notice that the factor x minus r appears as a factor m times. In other words, x minus r to the power of m is a factor of f of x. So let's look at x minus r to the power of m. And just for the sake of our argument, let's just say that this is our f of x. F of x is x minus r, the whole thing raised to the power of m. So that essentially means that we have x minus r times x minus r dot 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 times x minus r. We have x minus r times itself m times, m factors of x minus r. And in each one of these factors, the real number r appears as a real zero. So r appears as a real zero here, r appears as a real zero here, r appears as a real zero here, r appears as a real zero m times. And because of that, we call r a real zero with multiplicity m, or r has multiplicity of m as a real zero. Let's take a look at some examples. Let's take a look at some examples. F of x equals x squared plus 4x plus 4. We can probably factor this without too much trouble. This looks like it's x plus 2 times x plus 2. Is that right? 2x plus 2x is 4x. 2 times 2 is 4. Yep, sure enough. Now, what is the only real zero of this polynomial? Let's see. If I plug in x equal -2, that makes this 0, that makes this 0. Okay. When we talked about roots of multiplicity m, we had it in the form of x minus r to the m power. Okay. So if I'm looking for the roots here, I guess I need to write this as x minus something to a power. Okay. And this would be x minus -2, x minus -2. R equal -2 is a real zero of this function. If we plug in -2, we get 0. This is a, whoops, I said root. Our author doesn't use that word. A real zero. This is a real zero of multiplicity 2. Let's look at our next example. Oh, is this what I think it is? I know what this is just because it's a form that I recognize. But let me try plugging in the whole number factors of this, the constant term, and see if I can get 0. The whole number factors of this term are plus or minus 1. So let me try that. Let me plug in 1. And I get 1 minus 3 is -2. Plus 3 is plus 1. Minus 1 is 0. Okay. I plug in x equal 1, and that makes f of x 0. That means that x equal 1 is a real root. I'm sorry. I plug in 1, and that makes this polynomial 0. So that means that x minus 1 is a factor. It turns out this is the only factor, and it occurs 3 times. So x equal 1 is a real 0 and I'll say of multiplicity 3. And the reason I say multiplicity 3 is because this factor, x minus 1, appears as a factor 3 times. So the real 0, 1 appears as a real 0 3 times. What this is, really, is x minus 1, x minus 1, x minus 1. So here 1 appears as a real 0. Here 1 appears as a real 0. Here 1 appears as a real 0. The real number 1, x equal 1, appears as a real 0 3 times. It has multiplicity 3. This is kind of complicated, I think. I want to find the real zeros. I don't have any idea how this factors. So what I'm going to do is I'm going to take the whole number factors of minus 3 and plug them in one by one and see if any of these will make the polynomial 0. So let's see. Plus and minus 1 are factors, and plus or minus 3 are factors. Let's try plus 1. I plug plus 1 in here and I get 1. Minus 1 is 0. Minus 5 is negative 5. Minus 3 is negative 8. Well, I sure didn't get 0 that time. Let's try plugging in negative 1. Negative 1 cubed is negative 1. Minus negative 1 squared is negative 2. Minus a negative 5. So let's see, let me write this down. I'm going to get negative 1 minus 1. And I have negative 5 times negative 1, which is plus 5. And then I have minus 3. That adds up to 0, doesn't it? So when I plug in negative 1, I get 0. So that means that x minus a negative 1 is a factor. Let me try plugging in the factors of 3. If I plug x equal 3 in, I get 3 cubed, which is 27. Minus 3 squared, that's negative 9. Minus 3 times 5 is minus 15, minus 3. What is that? Negative 3 minus 15 is negative 18, minus 27. Plus 27 is 0. Okay. When I plug in x equal 3, I get 0. So that means that x minus 3 is a factor. I've got 2 of the factors. I don't know what the third one is. Let me see if I can just figure it out. This is really x plus 1 times x minus 3 times something else. And whatever goes here has to multiply by x and x to give me x cubed. So what do I put here so that when I multiply it times x, in other words, what do I put here so that when I multiply it by x squared, I get x cubed? Shouldn't there be an x right here? X times x is x cubed. Okay, looking good. And whatever goes here, I have to be able to take that thing and multiply it by negative 3 and by 1 and get negative 3. So in other words, I have to take this times this and multiply it by something here to get negative 3. This times this is negative 3. So what do I multiply negative 3 by to get negative 3? 1, right? Okay. So that's the complete factorization of this thing. Now I'm doing this because I want to know the real zeros of this function. So first of all, let me combine these two terms into one, sort of. I'll write it as x plus 1 squared. And now something is a real zero of a polynomial if x minus that something is a factor. So I need to rewrite this as x minus something. X minus a negative 1 squared, x minus 3 to the first. Three is a root. No, I don't use that. Our author doesn't use that word. 3 is a real zero of multiplicity one. It just occurs one time. Unlike this guy, negative 1 is a real zero of multiplicity 2. We're interested in the multiplicity of real zeros because they have an effect on the shape of the graph of the function. That's why we're interested in the multiplicity of real roots. Multiplicity of roots and the graph of a polynomial. And let's look at our first case. Our first case, R is a root of even multiplicity. In other words, x minus r occurs as a factor twice, or x minus r occurs as a factor 4 times, or x minus r occurs as a factor 6 times, etc., etc. X minus r occurs as a factor an even number of times. And it's interesting what happens. R, and I better be specific here, R is a real root of even multiplicity. And if R is a real root, then it's an X-intercept. But here's what's interesting. If R is a real root of even multiplicity, yeah, R is an X-intercept, but the graph of f of x does not cross the x-axis at r equals 0. R0 is an intercept, an X-intercept, so the graph touches the x-axis at the point R0. But in this case, the graph of f of x doesn't cross the x-axis at the point R0. Now, how on earth could that happen? But let's just draw a picture of the two ways that this could possibly happen. Here's the point R0. And the graph of f of x touches the x-axis at this point. This is an x-intercept. The graph touches the x-axis at this point, but it doesn't cross the x-axis. So what happens is the graph has to come down like this and touch the x-axis. It kisses the x-axis right here, and then turns around and goes back up. That's the first scenario. And the second scenario is an analogous case. Here's R0 again. The graph of f of x touches the x-axis here, but it doesn't cross. So if the graph doesn't look like this, then the graph is going to have to look like this. It comes up and just touches the x-axis right there, and without crossing the x-axis, it turns around and goes back down like that. So if R is a real root of even multiplicity, x minus r squared, x minus r to the fourth, x minus r to the sixth, the graph either looks like this or it looks like this at the point R0. R0 is an x-intercept, but mysteriously enough, the graph doesn't cross the x-axis at the point R0. So the graph either lies above the x-axis and just touches at the point R0, or the graph lies below the x-axis and just touches the x-axis at R0. So that's what happens when we have a real root of even multiplicity. Okay, the second case, R is a real root of odd multiplicity. So the factor of x minus r occurs as a factor once, or it occurs 3 times, or it occurs 5 times, or 7 times. So in each case, we have x minus r raised to an odd power. And in this case, r minus 0 is an x-intercept, as we would expect. R is a real root, so the point R0 is an x-intercept. And it's also true that in this case, the graph of f of x crosses the x-axis at the point R0. And again, we have 2 scenarios. These are a lot easier to imagine than what we had before. The graph comes up from underneath and continues to cross going upward, or the exact opposite happens. The graph approaches from above, goes through the point R0, and continues on its merry way going down. So this is the difference graphically between a root of even multiplicity and odd multiplicity. Where we have a root of even multiplicity, the graph touches the x-axis, but it doesn't cross. Where we have a root of odd multiplicity, the graph touches the x-axis and continues to cross. Our author or authors talk about turning points of a polynomial's graph. A point Pf of P is a turning point of the graph of the polynomial f of x exactly when the graph of f of x changes from increasing to decreasing, or vice versa, at the point P f of p. Now remember, increasing means going uphill from left to right. Decreasing means that we go downhill from left to right. In this context, we're always going from left to right. So we can say that the point P f of p is a turning point on the graph of a polynomial. Exactly when the graph of f of x changes from going uphill to going downhill, or vice versa, going downhill and then going uphill. That's a turning point, right where that change happens. So let's look at some turning points and some points that aren't quite turning points. Let's look at our first example. Here f of x equals x squared, and here's the graph of f of x equals x squared. Here the graph is decreasing. We're going downhill. Here the graph is increasing. We're going uphill. And right here at the point 0, 0, the graph changes from going downhill to going uphill. In calculus lingo, the graph changes from decreasing to increasing. So 0, 0 is a turning point. Another example. F of x equals 1 minus x squared. Now, what does that look like? We may know what this looks like, we may not. So let's just do this the way we've been doing it, okay? The first thing we'll look at is the basic function x squared that's in our repertoire. F of x equals x squared. Zero, 0. This is what x squared looks like. Now, I'm going to modify that by multiplying by -1. When we multiply the graph of a function by -1, what does that do? Doesn't it flip it about the x-axis? So it's going to take this graph and rotate or revolve it or reflect it about the x-axis. And now we're going to add 1. We're going to take this graph, -x squared, and essentially what we're doing is we're adding 1 to this graph. This is a vertical shift. One unit up. So we just take this graph and move it 1 unit up. This is the graph of 1 minus x squared. What do you think? Do you think that this graph has a turning point? Looks like it, right? Right here at the point 0, 1. And here we're going uphill. And over here we're going downhill. Or in calculus lingo, we're increasing and then we're decreasing. So yeah, the graph changes from going uphill to going downhill right at this point 0, 1. So the point 0, 1 is a turning point. Let's look at another example. This is the graph of x cubed. And right here at the point 0, 0, it looks like the graph comes up and sort of levels off here for just a bit and then continues on its merry way. Now, does the graph actually change direction here? Does it change from going uphill to going downhill here? Is it going downhill anywhere? No, actually, this graph is going uphill the whole way, isn't it? So even though the graph appears to level off just for a split second right here, there's no change of direction. Right here, the function is going uphill. And right here on the other side of the point, the graph is still going uphill. So this graph goes uphill the whole way. There's no change in direction. So there's no turning point on this graph anywhere. Polynomials and turning points. Just a few basic things that we might want to know. A polynomial of degree n can have at most n-1 turning points. It may have less than n-1, but n-1 is the most that it can have. So let's say n equals 3. We have a polynomial of degree 3. It can have at most n-1 or 2 turning points. A polynomial of degree 3 can have at most 2 turning points. It may not have that many. A polynomial of degree 8 can have at most 7 turning points. It may not have that many. A polynomial of even degree, 2, 4, 6, must have at least 1 turning point. So a polynomial of degree 4 got to have at least 1 turning point. A polynomial of degree 12, it's got to have at least 1 turning point. A polynomial of odd degree, 1, 3, 5, 7, may not have any turning points at all. It may not. And we just saw an example where that happened. We saw the graph of f of x equals x cubed, a polynomial of degree 3. It had no turning points. So a polynomial of odd degree may not have any turning points. Or it may have as many as n-1. Let's just look at a few scenarios. Something else, I'm not sure I mentioned this a minute ago or not, but let me mention it. A polynomial of even degree must have an odd number of turning points. This will make sense, I think, once we consider what our author calls, what does our author call this? The end behavior of polynomials. A polynomial of odd degree must have an even number of turning points. Again, this will make sense once we consider what the author calls, what does he call it again? The end behavior of a polynomial function. Let's consider an example. Look at this polynomial. It's of odd degree. The degree is 7. What else do we know? It's of degree 7, so it can have at most 6 turning points. Since it's of odd degree, it may not have any, but it must have an even number. So 0 turning points, 2 turning points, 4 turning points, 6 turning points. Those are all possibilities. Let's look at another one. Okay, this one is of degree 8. So this is even degree. It must have at least 1 turning point. May have as many as, let's see, 1 fewer than the degree. May have as many as 7 turning points. Must have an odd number of turning points because the degree is even. Let's look at some more things. Some qualitative properties of the graphs of polynomials. Just features that we can't measure mathematically, but we just observe qualitatively. First of all, the graphs are what we call smooth. The graph of a polynomial has no jagged edges. The graph does not come to a sharp point. There's no point on the graph where you could take your finger and prick your finger and go, I'm bleeding. All of the edges, etc., are smooth, rounded edges, no jagged edges, nothing like that. And we'll consider what that means in a minute via example. The second qualitative property that we want to observe about the graphs of polynomials. The graph of a polynomial is one connected piece. In other words, you can put a pencil on any point of a graph of a polynomial and move that pencil along the graph and get to any other point on the graph of that polynomial without lifting your pencil off. You can get from one point of the graph to another point of the graph by moving your finger along the graph, and you'll get to that other point. There are no interruptions, no breaks in the graph of a polynomial. They're one piece, one connected piece. Now let's look at some examples. Which of these graphs could be graphs of polynomials? Well, this graph is smooth. There are no jagged edges. And it's one connected piece. This could be the graph of a polynomial. What about this graph? Yep. I was going to comment further, but I'll save that for later. Could this be the graph of a polynomial? It's one connected piece, no sharp edges, no jagged edges. This could be the graph of a polynomial. What about this thing? Well, it's one connected piece, and there's no sharp edges, no jagged edges. This could be the graph of a polynomial. All of these could be graphs of a polynomial. What about the graphs of these functions? Based on the graphs, which of these could be polynomials? Well, what about this first one? You know what I see? This graph consists of two disconnected pieces. This is not a polynomial. Two disconnected pieces. And the problem occurs right here. This is where the disconnection appears. We've got a big break or an interruption in the graph, and we might mention that too. Where we have a break in the graph, that pretty much means that we're going to have at least two disconnected pieces. Now, what about this interesting piece of artwork? Tell you what, let me do this first. Could this be the graph of a polynomial? Let's see. The graph's one connected piece, all right, no problem there. But what if I take my finger and go, ooh, it's bleeding. I just pricked my finger on this jagged edge right here. Oh, the graph has a jagged edge. It's not smooth. Not a polynomial. The reason is jagged edge, not smooth. This could never be the graph of a polynomial. And what about this guy? The graph is one connected piece, but we've got a jagged edge there. It's not smooth. It's not a rounded edge here. So this fails the polynomial test also. Not a polynomial. And the reason is we have a jagged edge. Not smooth. So qualitatively, these are some of the things that tell us which graphs of functions could be polynomials and which graphs of functions could not possibly be polynomials. Now, at the end of this lecture, we're going to talk, what does our author call this again? At the end of our lecture, we're going to talk about end behavior. Okay, here we come to the end behavior of a polynomial graph. And here's the fact of the matter. A polynomial of degree n can have at most n real zeros and at most n minus 1 turning points. A polynomial of degree n can have only finitely many real zeros and only finitely many turning points. So there has to be a leftmost root or turning point, and there has to be a rightmost real zero or turning point. Going from left to right along the graph, we're going to hit the first turning point or real zero. This is our leftmost point. And we keep on going, and eventually we're going to hit the rightmost of these turning points or real zeros, which means that I can take my red marker and I can enclose all of my real zeros and all of my turning points in a box. And you know what? Maybe I'll enclose them with a black marker too, considering what it is that I'm about to do. So this black box contains all of my real zeros, all of my X-intercepts, and all of my turning points. Now, what does the graph look like inside here? Well, if there are turning points, it's going to go up, it's going to go down. It's going to cross the x-axis wherever there's a real root, and so forth and so on. A lot of things can go on here. The graph can go up. There can be a turning point, and then it goes down, and then it may go up again. Depending on the polynomial that we're working with, a lot of different things can happen here. But outside of this box, what happens to the graph of the function is no mystery. Outside of this box, a polynomial of degree n has a graph that behaves like the graph of f of x equals x to the n. Outside of this box, a polynomial of degree n has a graph that behaves like the graph of f of x equals x to the n. Let's look at some examples. By the way, this is what the author refers to as the end behavior. Go out past the end of this box this way, and the graph behaves like x to the n. Go out past the end of the box this way, and the graph of f of x behaves like the graph of x to the n. Let's just look at some examples, okay? Consider this function. It's a polynomial. What does its graph look like? I don't know. Do I know where the X-intercepts are? In order to find the X-intercepts, I've got to factor this thing. I may not be able to do it. I can try plugging in the whole number factors of 5 and see if one of those makes the function 0. But that's not going to give me all of the factors in this case because we've got a polynomial of degree 7. 5 only has 4 whole number factors. And none of those may make the polynomial 0. A polynomial of degree 7, I don't know if I could find all of the real zeros. I'm not even sure I could find any of them. Does this thing have turning points? Might. Boy, they'd be pretty hard to find too. So what does the graph look like? I don't have much of an idea. I don't know if there are any real zeros or what they are. I don't know if this thing has any turning points. It's of odd degree, so it may not have any. I don't know. It's of odd degree. It may have 2, it may have 4, it may have 6 turning points. I don't know. But here's what I do know. Here's the origin. And all of the turning points and all of the real zeros can be encapsulated in some black box. Whatever the turning points are and wherever they are, whatever real zeros there are and wherever they are, I can draw a black box like this that contains all of them. Now, what goes on in this black box, I haven't got the foggiest idea. And if you put a gun to my head, you said, tell me what the real zeros are, buddy, or kiss your life goodbye. I may be kissing my life goodbye right now. A polynomial of degree 7, can I factor that? I don't know if I can. Can I find the real zeros? I don't know. Can I find the turning points? I don't even know if I could find those. I have no idea really exactly what goes on in this black box. But outside this black box, I do know what goes on. Very interesting. And to find that out, I compare what did I call this thing? I compare it to the power function. And I could compare it to f of x equals 8x to the 7th. We know what this looks like. When x is 1, f of x is 8. When x is negative 1, f of x is negative 8. And when x is 0, f of x is 0. Here's what my graph looks like. You know what? Let me draw a better graph than that. Let me draw a slightly better graph than that. I'll just change the scale on the x-axis just to reduce the clutter. Here's 1. Here's 8. Here's negative 1 and negative 8. 0, 0 is on the graph. 1, 8 is on the graph. And negative 1, negative 8 is on the graph. And we know the graph looks like this. Well, this graph shows us how every polynomial of degree 7 with leading coefficient 8 behaves outside of this black box here. Well, what happens as we move to the right and x goes to infinity? The graph takes up and goes toward positive infinity in the y direction. So as we move outside the box and x goes to positive infinity, the y value goes to positive infinity too. This graph goes to the right and it goes up. This graph is going to go to the right and it's going to go up. And we'd say as x goes to infinity, y goes to infinity. Now what happens over here? Well, our power function tells us how this graph is going to behave. This graph, outside of the black box, is going to do exactly the same thing that the graph of the power function does. Notice as x goes to negative infinity, the y value also goes to negative infinity. As we move to the left, the graph goes down. We move to the left, the graph goes down. So as x goes to negative infinity, f of x goes to negative infinity. What does the graph of this polynomial look like inside the black box? I don't know. It may have some x-intercepts. Where would they be? I don't know. It may have some turning points here. Well, where are they? I don't know that either. But I do know what this function does outside of this black box. as x goes to positive infinity, or as we move it toward the right, the graph goes to positive infinity in the y direction. As we move to the right, the graph goes up. And outside of this black box, as we move to the left, the graph goes down. As x goes to negative infinity, the y value goes to negative infinity also. Let's look at one more example. And I promise you, this last example will conclude our lecture. Let's suppose that f of x looks like this in its factored form, okay? Two is a real zero, and it has multiplicity 2. Three is a real zero, multiplicity of 1, and let's see, 4 is a real zero, multiplicity 1, and let's see, if I take this and multiply it out, I get x squared times x is x cubed times x is x to the 4th. This thing is a polynomial of degree 4. And I'll note for the record, it's of even degree. Now here, because I have the polynomial in factored form, I should be able to discern a lot more about the graph of this function than I could the function in our previous example. Here's the x-axis, and here's the y-axis. X equal 1, x equal 2, x equal 3, x equal 4, and here's my black box. Outside of the black box, f of x behaves like f of x equals x to the 4th. So this graph is going to go up like that, and up like that, because the graph of x to the 4th behaves like that. This is the graph of x to the 4th, and it looks like this. So outside of the black box, that's how this function is going to behave. 1 is a root of multiplicity 2. And I'll note even multiplicity. Do you remember what we said about a real zero that had even multiplicity? There's an x-intercept at that point, but the graph doesn't cross the x-axis at that point. So there are two possibilities here. We have an x-intercept, and the graph just kisses the x-axis here and turns around. It doesn't cross. So the graph can turn around and go like this. But we know that ultimately, outside of this black box, the graph has to go up like this. So is this a realistic scenario? Well, let's see. In order for the graph to turn around and come back up, oops, it's going to have to cross the x-axis right here, isn't it? But it doesn't cross the x-axis here. These are the only places. I'm sorry, I messed this all up. I apologize. I don't know why I was thinking x equal 1. Well, let me start over. X equals 2 is a real zero. Here it is, x equal 2, not x equal 1. It has even multiplicity. So it's either got to kiss the graph like this and turn around. But outside the black box, the graph is going upward this way, which means that if this is what the graph looks like at x equal 2, the graph has to turn around and come back up and cross the x-axis again. And there's another intercept here. But can that happen? No. We have all of our real zeros, 2, 3, and 4. These are all of the real zeros that we have. So the graph can't come down like this and then come back up and cross the x-axis, which means that right here at x equal 2, the graph can't look like this. So what happens then? Well, it's true. The graph does kiss the x-axis right at this point. The graph touches the x-axis at this point, but it doesn't cross. And it has to do it like this. And the graph has to go upward this way and continue out of the black box and go like this. Now, the graph has to cross the x-axis at 3. So guess what happens? We have to have a turning point here, at least one, somewhere between 2 and 3. And then let's see what has to happen now. The graph crosses the x-axis. How do I know it crosses the x-axis? Because 3 is a real zero with multiplicity 1. Odd multiplicity. Which means the graph crosses the x-axis here. Okay. We have a real zero at 4, and the multiplicity is 1. It's odd. So the graph has to turn around and cross the x-axis here. And there are no more x-intercepts, no more real zeros. And let's see, how many turning points do we have here? We have 2 turning points. And we don't have a turning point here because this is a root of multiplicity 0. So this graph, we know it has to continue upward like this because it imitates the graph of f of x equals x to the 4th. This graph crosses the x-axis and goes upward at x equals 4. And outside of the box, that's exactly what the graph has to do. It has to go up. So this thing is just going to continue to go up. So here we have a pretty good idea of what the graph of our function looks like. And you know something? Our end behavior, what the graph does outside of the black box, helped us to figure out whether the graph goes like this at x equal 2 or whether it goes like this at x equal 2. So what the graph does outside of the black box, what our author calls the end behavior, that can be pretty important. And behold, that's what the graph of our function looks like. Because we knew what the roots or the real zeros were, we had a good idea, or we were able to figure out anyway, what happens inside this black box. And what happens outside the black box? Outside the black box, this function of degree 4, even degree, has to behave exactly like f of x equals x to the 4th. This is the whole reason that we study power functions. A polynomial of degree 4, which is what this is, outside of the black box, it has to behave exactly like the corresponding power function x to the 4th. A polynomial of degree 4 has to behave like the power function x to the 4th outside of the black box. Inside the black box, we figured out the real zeros and the turning points. Outside the black box, we referred to the corresponding power function x to the 4th to tell us what happens outside the black box. Just as this graph goes to the right and up, this graph outside the box has to go to the right and up. Just as this graph goes to the left and up, outside the box, this graph has to go to the left and up. Okay, that's it. End of our lecture.